Today we'd like to look at a few more interesting things that happen because of refraction. And the one we'd like to look at first is this graph of refractive index versus wavelength for water. And the thing I want you to realize is that the index of refraction is not a constant. I know we saw for air that it changed based on temperature, pressure, and relative humidity, but that's not even what I'm talking about now. I'm talking about if you have water and you hold the temperature and pressure constant, you don't add any impurities to the water, you still get different refractive indices based on different wavelengths of light. You can see it's a very dramatic change when we're about 200 nanometers. That is ultraviolet light. You can see visible light starts around 400 nanometers, and you can see that the index of refraction is pretty close to 1.35, so 1.34 something. We can see that when we leave white light, okay, when we're at the red end of the spectrum, we're closer to the 1.33 that we are used to. So the index of refraction of light changes depending on the color of the light that's passing through the material. That would mean that light travels faster when it's red light versus violet light when it's passing through water. All right? Not only does it mean they travel at different speeds, but it means that they're going to bend by different amounts when the light enters the water. It's because of this that we can take a piece of glass like a prism, and we can have the light enter the prism and break up into the individual colors. Since they each have a different index of refraction, they are each going to bend at a slightly different angle. So the white light will separate out into the other colors based on index of refraction. This was first done by Isaac Newton, or at least first interpreted by Isaac Newton, and he realized that white light was composed of all the colors of the spectrum. He could take white light and break it up, or he could take the different colors of light and put it back together and turn it back to white light. He published his results in a book in 1704 called Optics. Oftentimes you'll see pictures like this. This is a bad representation of what's happening. It leads us to believe that the colors don't occur until it leaves the prism, and that's exactly wrong. That the separation of colors happens as soon as the colors enter into the prism. Each color bends at a different angle because they each have a different index of refraction, and because of that they each go in a slightly different direction. It might become more exaggerated when it leaves the prism, but it starts as soon as it enters the prism. This is a much better representation of the phenomenon. We can see this when we look through our fish tank, because this will happen with water, as we mentioned before. Water has different indices of refraction for different colors. And I'm looking at a white light bulb, and you'll notice that the white light bulb is broken up into the individual colors that make it up. Again, viewing it through a fish tank. Here's my overhead lights viewed through the same fish tank, and you can see again the different colors of the spectrum. If you take a white line from my board like this, and you view it through a prism or through the fish tank, you can see that this also will break up. But when you break it up, you'll notice that it actually just has three colors: blue, green, and red. And that's because in order to make all the different colors, you only need your three primary colors. So the LEDs that make up this board only need to produce red and blue and green in different amounts, and they can create any of the colors of the spectrum. Okay, this idea that light will refract differently for different colors can cause problems when you're making lenses for telescopes or lenses for cameras, it can create an effect that's known as chromatic aberration. And what this means is the colors are being refracted differently, so they do not all focus at the same location. When you have a lens where this is particularly troublesome, you're going to see objects, especially far away objects, having a side that looks red and a side that looks blue or purple. So this is something that you want to avoid. You can avoid it by choosing the right kind of glass. You can't totally eliminate this effect, but you can limit it. Okay, so if you're looking at these different types of glass, you definitely would not want to use this curve. This is dense flint glass, and if you notice, visible light runs from here to here, and you can see it's a dramatic change in refractive index. Something more along the lines of this bottom curve would be much more desirable, because even though it might not bend the light as much, the separation between the violet end and the red end will be a lot less. There's not as big of a difference in the index of refraction. This material might be really good if you're trying to make a prism where you want to split the light up into the different colors, but this material would be better if you're trying to minimize that effect. We also see this idea of white light breaking up in the colors with our rainbows. When you look at a rainbow in the sky, first thing you should realize is the sun is always going to be behind you. So if you're looking at a rainbow in the east, the sun will be in the west. The sun, in fact, if you continue to straight line through your head, would be right at the center of the bow. Realize the bow is actually a circle, and that circle is interrupted by the surface of the earth. Now realize when you're looking at the rainbow, some drops of water, like the ones I have circled here, will appear to be red to you. Some drops of water will appear green, some will be blue and violet, and so on. Even though each drop of water will appear a different color to you, realize that all the drops are producing all the colors. So when white light comes from the sun, again, which is behind your head, enters the drop, it splits up into the individual colors, hits the back of the drop, bounces off, comes out, and heads toward your viewing location. Notice that only the blue light is going to enter my eye. So this drop would look blue to me. Someone who is standing in a different location may see that drop as red or purple or green or not at all. Okay, depending on exactly where they are positioned. We can create rainbows from fountains or garden hoses. We just have to make sure we remember to keep the sun lined up behind us. Okay, and here are some pictures of rainbows that people have sent me through the years. All right, and that's where we're going to end for today.